All right, last 20-ish slides of chapter 11. We talked about valence bond theory last class, and now we're learning about molecular orbital theory. So MO theory, which if you take more chemistry will get covered in more depth, works for the entire molecule instead of just for atoms. We're going to be looking at relatively simple examples for molecular orbital theory. Something that you would learn if you took physical chemistry is that the Schrodinger equation, figuring out like characteristics about the electrons and stuff in an atom, even in an atom, a relatively simple atom, is either difficult or impossible, and when you ramp that up to a molecule, you just can't do it. It's not possible to do. And so basically they make an approximated guess. Hey, how does this function that we came up with fit for our solution? And then they do a bunch of stuff with computers. And so obviously we're not going to do that. Instead, we are going to do some qualitative learning about linear combination of atomic orbitals. So the linear combination part basically means adding or subtracting, sort of. We're not like multiplying orbitals together. And the combination of atomic orbitals, we're going to be taking two atoms and combining those orbitals that they have to form a couple of different orbitals, molecular orbitals. So we're going to combine the valence atomic orbitals like S and P for all the atoms in the molecule. And we'll learn some qualitative stuff about it. We're not going to do very much, if anything, with numbers, at least not difficult numbers. So with valence bond theory, we were hybridizing the orbitals for just the central atom, the one atom in the middle. And this will be for, basically for us, two different atoms. Our first example of the linear combination of atomic orbitals, LCAO, is H2, kind of our simplest molecule. One of the molecular orbitals that we can come up with is if both of our 1s orbitals are in the same phase, if they're in sync. That's sort of like adding them. And because they're in sync, because they're, whatever their waves are overlapping in a good way, it lowers the overall energy because of that interaction. And we would call this a bonding orbital. And this is our sigma 1s. The sigma relates to the shape of the orbital. And overall, this bonding orbital is lower in energy than the individual atoms by themselves. So it's favorable to make a bond. I said adding and subtraction earlier. The other thing that we can do is basically subtraction. So we can also have the anti-bonding orbital, which we can sort of think of as them being out of sync or out of phase. One of the analogies that I came up with that I thought was sort of helpful is when you are walking, your arms normally move at like related to the way that your feet are working. If you're holding hands with somebody, they're also walking, if you're both walking, right? And if your feet are not synced up, your arms will swing at different paces. And if they are nicely synced up, then you're holding hands and they are both swinging in the same pace, right with your stride. That's sort of like what we were seeing with the bonding orbital. They're right in stride. If you're out of stride, you can be perfectly out of stride, and then one of you, your arm wants to go forward and the other wants to go back, and that's not quite as relaxing. So this is sort of like being out of phase. It's also kind of like when you're around people that know you really well and you get along. The bonding phase, you kind of finish each other's sentences, right? The knowledge that you have about each other, you can kind of contextually help each other with things. It makes it easy to get along sometimes. Alternatively, you could not get along, and then they really know how to push your buttons, and that might be like our anti-bonding orbital. So this is a higher energy orbital because there's no overlap and they're completely out of sync, represented by the different colors here. And the star is for the anti-bonding. So if we don't have a star, that means it's bonding. If we have a star, it's anti-bonding. The anti-bonding is always going to be higher in energy than the bonding because they're out of phase. And we'll typically show these both together, which we'll see in a bit. This is just kind of a summary. So what we put together for molecular orbitals is an MO diagram. And this is a relatively simple molecular orbital diagram. They can get really hairy. We won't be looking at things that are a lot more difficult than this. Again, we're just adding two things together. So in this case, we've got H atom number 1 on the left, and we've got hydrogen atom number 2 on the right. So that's what we would start with if we were putting this together from scratch. We would start with our hydrogen atom on the left, our hydrogen atom on the right, and then how do those interact with each other? Since they're just 1s, this is about as simple as it gets. They're either bonding, and it's a sigma bond that they're forming, and it's made up from the 1s, so the 1s subscript. There's also the anti-bonding that can form, which is sigma star 1s. So we would draw those in, and since we've got our orbital diagrams from our atoms, we can dump these electrons into these starting from the lowest energy and filling our way up. In this case, both of our electrons fit into the bonding orbital. If we had more electrons, more of those electrons would go into, I'll say extra electrons. Extra electrons would go into the sigma star 1s. Again, sigma is basically just our single bond, where we've got complete overlap of our orbitals, whereas we'll have pi bonds later, and those are where they're just next to each other, and they're overlapping side to side. And because they're dumping both of their electrons in, and this bonding orbital is lower, it's more stable for them to be in the bond. So the relatively simple math, this is, I think, the only math that we're going to do for molecular orbital theory, is bond order. So how bonded are the two things? And it's the number of electrons in the bonding, MOs. In this case, that was both. Subtracted from that is our anti-bonding electrons. We didn't have any, right? Our anti-bonding box was empty up here. So we had 2 in our bonding, 0 in our anti-bonding, so we do 2 minus 0, and then we divide it by 2, because there's 2 electrons per what we would think of as a bond. Whenever we have a positive bond order, we will form a bond. In this case, we've got a bond order of 1 that corresponds to basically a single bond. If we had a bond order of 2, that would be a double bond, and 3 would be a triple bond, and we can also have halves as well. If our bond order is 0, which we'll see an example of, or negative somehow, then we will not form a bond. So for example, we can do a molecular orbital diagram for a diatomic helium molecule. So if we were putting this together by ourselves, we would draw our first helium atom on the left, our second helium atom on the right, just to start. And we would say, well, how are these going to interact with each other? They're just 1s orbitals. So we would produce 2 boxes, because we've got 2 boxes. So one of those would be our bonding orbital, and one would be our anti-bonding orbital. Bonding is always going to be lower in energy. Anti-bonding is always going to be higher in energy. And we've got 4 electrons total. So we dump 2 of those electrons into our bonding and 2 of them into our anti-bonding. And since we have 2 in our bonding and 2 in our anti-bonding, 2 minus 2 is 0. If you divide that by 2, it's still 0. So no bond will form. Or rather, no bond is formed. Questions so far? If we have diatomic helium, but it's an ion, that would have a predicted bond order of 1/2. So on the right, we have our helium ion, which would probably take a lot of energy to produce. So we've knocked off 1 electron. So we've only got 3 electrons to put into our boxes now. So we put 2 into our bonding, and then the last one gets into our anti-bonding. We would do 2 minus 1 for 1 on the top, divided by 2 for a bond order of 1/2. Question?
For Ag2 plus, why would both of them be Ag plus on the diagram?
Since we just have a 1 plus, that means that we just lost 1 electron rather than 2 electrons. He2 plus would be both of them have just 1. And this allegedly exists. I've never seen it. All right, so linear combination of atomic orbitals, molecular orbital theory. Summary. Our molecular orbitals we can approximate, we can just kind of roughly say that they're a linear combination of our atomic orbitals. Bonding and anti-bonding. Those aren't our atomic orbitals, but those are our linear combinations. The number of molecular orbitals formed is the same as the number of atomic orbitals, just like with our hybridization in valence bond theory. So if we have 2 atomic orbitals, then we need to have 2 molecular orbitals. Partly, you can think of that as like we just need somewhere to put the electrons. If we had 4 electrons in our helium, diatomic helium molecule, and we just had the 1 bonding orbital, you can't fit 4 electrons into 1 orbital. So we have to have 2 orbitals. When our atomic orbitals, like our 1s orbitals, combine and form our molecular orbitals, one is lower in energy. That's our bonding. Bonding is favorable. And one is higher in energy. That's our anti-bonding, which kind of offsets the benefit of the bonding. And we are going to fill the lowest energy molecular orbitals first. Bonding, usually. And we're still following Hund's rule, where when we're filling molecular orbitals of the same energy, we will fill them in singly first with parallel spins. We'll see some examples of that. And positive bond order exists. 0 bond order does not form, or does not stick around at least. So that's the very basics. All right, use molecular orbital theory, draw out a diagram if you'd like to predict the bond order in a diatomic hydrogen ion. Is the H2 plus bond stronger or weaker than the H2 bond? If we want to draw out a diagram, we're going to start with, since it's hydrogen, we have access only to our 1s orbitals. One of them will be hydrogen, and the other one will be H+. How many electrons does hydrogen have? 1. How many electrons does H+ have? None. So we've just got 1 electron, and when these combine, they're going to form some molecular orbitals. We'll have our sigma 1s, sigma because it's direct overlap, that's like our single bond, and 1s because they're made up of 1s atomic orbitals. And we'll also have sigma 1s with the star, that's our anti-bonding orbital. And then we'll put our electrons in starting from the bottom. We just have 1 electron, so that's pretty easy. So we've got how many bonding electrons? 1. We have 1 electron in that bonding orbital. And how many anti-bonding? 0. And we divide that by 2, so our bond order is 1/2. Is that stronger or weaker than our H2 bond? If we had H2, instead of H+, we would have H, so we would have another electron in this right atomic orbital. That would go into our bonding, so we would have a bond order of 1. since we just have the one electron, our bond order is 1/2. So this is weaker than H2.
The higher the bond order, the stronger it is.
Correct. Yeah, higher bond order is stronger, lower bond order is closer to not existing, which would be 0 or negative. So that's our simplest case. We can also do stuff with bigger atoms. So moving down to period 2, homonuclear diatomic molecules, just we have the same nucleus, the homonuclear part. So we're using the same element. All right, so the next set of molecular orbitals that we come up with, we've got 2s, and those are going to combine just like our 1s. So we'll have our bonding 2s, and that's a sigma bond, and our sigma starred 2s, which is our anti-bonding orbital. And based on this molecular orbital diagram, this predicts that lithium can bond with another lithium atom, and that apparently exists in the gas phase. Since lithium is normally a metal, it would just exist as a metal, which isn't really bonding in the same way. If we move over one spot to beryllium, so we're number 4 on the periodic table, we do the same thing. We have our bonding and our anti-bonding. There's still sigma bonds. And since we've got a total of 4 electrons to dump into 2 molecular orbitals, we end up with 2 bonding, 2 anti-bonding, so a bond order of 0. So we would not expect beryllium to exist as a diatomic molecule. When we move over one more spot to diboron, B2, we combine the 2p atomic orbitals pairwise. So we're going to just pick the x direction ones to be the ones that are connecting or pointing in the same direction of the different nuclei. And we'll have a bonding version where we've got good overlap, and the anti-bonding where they do not connect. And then the other 2, so if the x ones are the ones pointing at each other, those would be like in the plane. We would also have 2 that are coming from the top and the bottom. That would be another combination of px. We'd have one that's coming out of the board and going into the board. Those would be our other 2 sets. Or rather, they would be side by side and side by side this way, instead of being like this or this. Because we've got 2 balls. Here. Let me pick up my pencil and I'll draw it. Let's do orange, go Tigers. So these might be our PZ orbitals, right? So they're not going to have direct overlap, like our PX is going to have direct overlap. And then we would also have PY coming out of the board. And going into the board. And those are also not going to have direct overlap. And this is what we see sort of here. So since they're in this side-by-side orientation, these get assigned the pi symbol instead of the sigma symbol. So we'll have two of them, one for the y, one for the z. And those are equal in energy because they're just rotated from each other. And we also have the anti-bonding ones where they're kind of splayed apart from each other. The bonding ones are where they overlap. So this is sort of similar ideas to what we saw in valence bond theory. Here's that other pair. Since they differ only in the way that they're oriented, either up and down or front and back, they're going to have the same energy. And we can get the relative energy from calculations, computations. B, C, and N have a different order than oxygen, fluorine, and neon. That's the most that you might have to memorize. Is that the sigma and the pi bonds are just flipped. So for one of those, maybe the sigma will be lower. For the other one, the sigma will be higher energy. We'll see pictures of it or diagrams. Our typical energy ordering is that our sigma is lower in energy. That's direct overlap with our valence bond theory. When we were looking at single bond versus double bond, we saw that with a sigma bond, a single bond, we had a certain amount of energy. If we added the pi bond on top of that, the second bond, the double bond part, it didn't double the energy of the bond because it's a different type of bond. It's weaker, it's not direct overlap. And then our other two, the anti-bonding forms, mirror the bonding order. So our expected order is over here on the right, where we've got our sigma overlap, lower in energy, that's our direct overlap. We expect it to be stronger because it's direct overlap instead of being side-by-side overlap. And then our pi bonding is slightly lower in energy. The anti-bonding is the same distance, just up, increased in energy. So this whole thing mirrors top and bottom. And that's what we would expect. For boron, carbon, and nitrogen, the mnemonic that the book has is be careful now, because the sigma and the pi bonding orbitals are flipped from what we expect. Questions? Confusions?
Why are they flipped?
It's a great question. I don't know. They're flipped because of the way that they are. Yeah, I couldn't tell you. Not my specialty. From what the slides say, it's because of increasing 2s, 2px mixing. Why that is? I don't know, because their size, maybe? But this is the only difference for those molecular orbitals. And this is what the molecular orbitals look like for those homonuclear, the B2, C2, N2, et cetera, homonuclear molecular orbital diagrams. So for boron, we've got, it's our first entry into our P block. So their atomic orbitals would look like that. R2s, R2p. And since our pi 2p is lower in energy for B, C, and N, we put them in singly first with parallel spins, and then we pair them up when we add 2 more electrons for carbon. And our bond order is 1 and 2 respectively. When we get to nitrogen, our bonding is full. It's the wrong labels, but. So we've got full bonding for N2, and that has a bond order of 3. If we did a Lewis structure for N2, we would also find that it has a triple bond. So that matches well. And then we have a smaller 2s, 2px interaction, I guess, for O2, F2, and neon 2. And we are adding more electrons. So we add our next 2 electrons into the pi 2p antibonding orbital. So we've got 6 bonding for all 3 of these. And for oxygen, we also have 2 in the antibonding, which gives us a bond order of 2. When we add 2 more electrons in, like for fluorine, we get a bond order of 1. And neon, just like our other noble gas helium that we looked at earlier, has a bond order of 0. So it's expected to not bond. One thing that's cool about the molecular orbital theory is oxygen, if you can get it into a form that, like a liquid, it's paramagnetic. So it will actually get attracted to a magnetic field. And if you remember our definition for paramagnetic from previously in the class, paramagnetic means we have unpaired electrons. This is not an expected result from our Lewis model. So in our Lewis model, all of the electrons are paired. We've got lone pairs, and we've got our double bonds. However, if we look at our MO diagram, we've got unpaired electrons in O2, which corresponds with it being paramagnetic. So that's one thing that's cool about molecular orbital theory. It also comes in handy when we're working with transition metals and the different compounds that they form. But that's beyond the scope of the class, fortunately. All right, here is a generic molecular orbital diagram for nitrogen. Fill it in for N2+, and is that going to be stronger or weaker than N2? Is it diamagnetic or paramagnetic? you were having trouble getting started, I've drawn in the atomic orbitals for nitrogen and the nitrogen ion. All right, so the way that we're going to fill these in is starting from the bottom and working our way up. Our electrons will like to get into the lowest energy spot as if they can. That's for our ground state, just like the way that we like to be in our lowest energy state, typically not up and running around unless we are actively exercising. My ground state is very comfy at home. Love my bed. All right, so 2 electrons get dumped into our sigma 2s. We have 2 more electrons in our 2s orbitals, and so those go into the anti-bonding orbitals. That's because our 2s for both of these is full. So 4 electrons in there. And then we've got our 2p electrons. We've got 5 of them. 1, 2, 3, 4. So we can get 4 of them into our pi 2p. And then our last one goes into the sigma 2p. When we're calculating our bond order, you can include these sigma 2s and sigma star 2s, or you cannot. It doesn't matter because they're full, so they're going to offset because we've got 2 and 2. So you can either do 5 in our bonding from our p orbitals minus 0 in our anti-bonding orbitals divided by 2 for a bond order of 2.5 or 2.5. Or you could have done 7 minus 2 over 2, which gets you the same result of 2.5. Is that stronger or weaker than N2? It is weaker. Why is it weaker?
The bond order of N2 is 3.
Yes, N2 has a bond order of 3. And is the N2 plus molecule diamagnetic or paramagnetic? It's paramagnetic. We have 1 unpaired electron. Diamagnetic is all electrons paired. Questions? So that's homonuclear. We can also have heteronuclear diatomic molecules. So different elements. Here's a molecular orbital diagram for NO, nitrogen monoxide. Oxygen is more electronegative. So its atomic orbitals are lower. So one takeaway here is that higher, I'll just write it out, electronegativity lowers the atomic orbital energy. How much lower? Some amount. We're not getting into numbers. So just as long as if you had to draw one of these out, for example, on an exam, just as long as you draw them lower, it's like a perceptibly lower amount, that's good enough. The lower energy atomic orbital, in this case, are oxygen atoms. They're closer to where our bonding orbitals, molecular orbitals, show up. They're going to contribute more. They're more similar because they're closer in energy. And the higher energy ones are closer to being the antibonding, and so they contribute more to the antibonding molecular orbital.
I have a question.
Yeah.
In the diagram for the sigma 2p, on the last diagram, it was 2 boxes, and the I2p was only 1 box.
Right, so in the last one we were looking at nitrogen, BCN. Be careful now. They flipped. Now we're looking at oxygen, which is the expected order. So that's why it's flipped back. Or we have an oxygen. So we're back to the expected molecular orbital order. We can look at the same thing for fluorine bonding with hydrogen. Fluorine's so much more electronegative than hydrogen, and so its 1s orbitals don't even make it onto the graph. So for our 2p interacting with our 1s can interact to form an antibonding and a bonding, and then we've got 2 leftover non-bonding orbitals. I wouldn't expect you to be able to come up with this by yourself in a vacuum. I feel like those should be backwards. Anyway, use the molecular orbital theory to determine the bond order of the FO minus ion. I feel like it should be OF minus, but maybe I'm wrong. Is the ion paramagnetic or diamagnetic? So if we were doing this, we would have, let's say, oxygen and F minus. Maybe the order is that way so that oxygen's the minus. Who knows? Let's do O minus. No. It doesn't matter. We'll do O minus. Oxygen normally has how many valence electrons? 6. We could also fill up its orbital diagram. That's the same. So we're going to put in 6. 6. It's a minus in this case, so for the minus, we add 1. Fluorine normally has 7. Also, that's just its electron configuration. So there's our starting points. If you were drawing this out by hand, we might maybe draw the atomic orbitals for fluorine a little bit lower. And then we get to combine all of the electrons. So for our sigma and our sigma star, those are full because our 2s orbitals are full. And then we've got 7 from each of our species, which gives us 14 to fill. 1, 2, 3, 4, 5, 6, 7, 8, 9. Nope, I counted wrong. There's 5. So we've got 5 times 2, there's all of our 10, because we filled some earlier. So we're using some of the similar ideas that we've used in the past. Hund's rule, the Aufbau principle, the building principle, where we fill them from lower energy to higher energy. What is our bond order? Yeah, our bond order is 1. A visual way to look at it is we've got our kind of baseline energy. Everything above this is antibonding, everything below it is antibonding. We've got 2 antibonding that match up with these 2 bonding, so those would cancel out, and we would just have the sigma 2p bonding left over. The writing it out way of doing it, we've got 6 bonding electrons minus 4 antibonding electrons. Divide that by 2. And you get a bond order of 1. Again, I'm omitting the sigma 2s and sigma star 2s because they cancel out. Is this ion paramagnetic or diamagnetic? Yeah, it's diamagnetic. Why?
Because there's no, they're all paired.
Yes, they're all paired. Questions? For polyatomic molecules, we're not going to do any MO diagrams, but we're going to talk about it briefly. Neither the Lewis model nor valence bond theory, which we've learned previously, predict that ozone O3 has 2 equivalent bonds. We've looked at it previously. The Lewis diagram is over here on the left, and our valence bond model kind of mirrors it, just with taking a look at our side-by-side overlap for our double bond. However, in molecular orbital theory, the pi MOs would be formed from a combination of 3 2p orbitals, and we would end up with a bond order of 1.5 for them, since we're considering the entire molecule rather than just looking at the central oxygen for its molecular orbital theory. So we'd have a bunch of boxes. This also helps for things like benzene, which is bad for you. Benzene's very bad for you. It's a carcinogen. Benzene has a structure that looks something like this, we can also draw it like this. So if we take these double bonds and rotate them all one position, then we get the other resonance form of benzene. And if we do a molecular orbital diagram, all of the pi bonds that are sticking up kind of all interact with each other, and so you can sort of think of it as like a racetrack for the electrons. They can just kind of run around freely. And because of stuff that we don't learn in this class, this is especially stable. And it's also carcinogenic because it's like this nice little flat molecule, and it can slip between your DNA and get stuck there. And then when things come along to like transcribe it or whatever, that can cause replication errors. It also doesn't smell good, if I remember correctly. Questions? That's it for MO theory. Okay.